warahmatullahi
Yes, we can see the screen, Professor.
ya, Pak. Show the presentation. Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Allahumma salli sadri wa yassirli amri wa hlul 'uqdatam min lisani yafqahu qawli. Ladies and gentlemen, our topic today is about Industrial 4.0, which one of the characteristics is the Internet of Things. Interdisciplinary fields that integrates science and engineering will lead to an application such as robotics. As we know, robots can be used in many situations for many purposes, such as in manufacture and surgical. Today, many of robots are used in dangerous environments, like in nuclear radioactivity, bombs detection, or in the place where humans cannot survive, such as in the space, underwater, or in the high heat. These utilizations require high control techniques in the real situations called nonlinear control. Before we begin, I have a few housekeeping notes. First, Q&A session will be held after the presentation ends, and the speaker will present the material for about 45 minutes. Ladies and gentlemen, our next speaker is a professor who was achieving very inspiring results studies, research goals, and was as well as publication records in the field of control engineering. And he got professorships for just only in 8 years after his BSc graduation. One of his specializations is nonlinear control, in which very adaptable to the application of robotics in Industrial 4.0 for those mentioned above. Ladies and gentlemen, moving along our session, please welcome Professor Saleh Mobayen.
Thank you very much for introducing me. Do you hear me?
Yeah, very clear.
Fine. Then we can start presentation. And thank you inviting me to this seminar. Okay, and now I think you can see my slides, yes?
Yes.
Okay, fine. In the name of God.
Presentation mode, Professor.
Can I start my presentation?
Yes, sir.
Okay, fine.
Yeah.
In the name of God, we will consider the design control of rigid robotic manipulators in this seminar. Actually, we will consider at first the design of the rigid robotic manipulators and the control of the robotic manipulators. That actually robotic systems, some are for walking robots.
Halo, Prof. Sepertinya terlempar.
Masuk lagi ya?
Disconnect kayaknya Pak. Mungkin
Terlempar sepertinya.
Sorry, I was connected. Unfortunately, do you hear me right now?
Oh yes,
Yeah.
Prof.
but no picture ya, Prof.
Screen still not appear. Sorry. Okay.
Okay. Do you see my slides right now? Robotic
Yeah.
systems. Okay.
Yeah.
Actually, we have some different types of robotic systems, such as walking robots, such as manipulators, robotic manipulators, and robotic arms, and human robots, and various types of robotic systems. Here we can see legged robots and wheeled robots here, and also we have different types of vehicle robots, such as autonomous underwater vehicle robot or unmanned aerial vehicle, or UAV systems such as quadrotors. And also we have some industrial robotic manipulators, such as these manipulators of different configurations. In the manipulators, robotic manipulators, we have rigid or flexible joints in the manipulators, and for the control of these joints, we have different ideas and different disciplines. And also, these are some special applications for robotic arms and robotic manipulators. For example, in jobs that are dangerous for human, this robot, the contaminating robot, cleans the main circulating pump in nuclear power plants. This is very dangerous for human, and we can use this robot for cleaning. And also, this is another application, another special application of a robotic manipulator for welding, for accurate welding, which is boring for human. Or this is another application for robotic manipulator for cleaning toilets, for manual tasks, which is hard for human. We have different types of robotic manipulators, such as Iskra robot, such as gantry, or vertical robot, and the three first ones are serial robots, are serial robotic arms, and also we have parallel robots. In the parallel robots, we use different joints, different links for doing accurate tasks with precision activities. Also, about components of industrial robotic arms, we have these parts. Actually, the first part is the mechanical structure or manipulator. The second part is actuators and sensors and the control system. In the robotic control loop, actually we have a set point or reference signal here for tracking purpose, signal. And using a compensator or controller. We have here controller. And here is mechanical manipulator or robotic manipulator. And here is output. And after controller, we have here actuators. And in the feedback loop, we have sensor. This is feedback loop for sensing the output of the robotic manipulator. And if here Y is the output, the actual output of the robotic manipulator, here will be measured Y. And if we have here reference signal is R, the error signal between measured output and the input will be R minus YM. And here is error. If the error signal goes to the controller and then the control input is U, U will go to the robotic manipulator. And also here we have some disturbances, some external disturbances or perturbations here. Some disturbance terms will be here. And also we have some noise, measurement noise by sensors or sensor noise. Here we will have sensor noise. In the robotic systems or each control system, we have different perturbations in the system, such as disturbances and sensors, which actually perturb the action of the system, the accurate action of the system. And we have two main goals. So the first goal is tracking the reference signal, and converging the error signal to zero. And the other goal or other purpose is to removing the disturbance and the measurement noise. We say them perturbations. Actually, we want to remove the perturbations of the system. Here we have different types of joints. We introduce the prismatic and the Revolute joints. The first joint is prismatic. Here we can see that its motion is prismatic or translational. And the second joint is Revolute or rotational. In the rotational, we have theta. The movement will be theta, will be. And sorry, do you hear me?
Yes, Prof.
Yes, Prof.
Yes.
Okay. And in the first prismatic motion, we have movement D. The movement is D here, and in the Revolute we have rotational movement. For the mechanical configurations, we have a different configuration for robotic arms. Actually, we have 5 different robotic configurations, such as Cartesian or prismatic, or PPP, and cylindrical, spherical, and jointed or revolute, and Iskara configurations. We have different types of configurations for actually various types of actions in the robotic manipulators. For the first configuration, we have here Cartesian or rectangular configuration. In this configuration, actually, we have PPP or prismatic configuration. Here we can see that actually here we have P movement around the Z, and the Y and the X movement around Y, another prismatic movement, and also another prismatic movement is around Y axis. Here is another type of Cartesian robot. Then when we say PPP, it means that it is prismatic, 3 prismatic motions. It is for Cartesian configuration. Another type of robots are cylindrical robots. They are RPP. Here, actually, the first motion is rotational or revolute, and the other motions are prismatic and prismatic. Then here is revolute R, and this one is prismatic P, and here is prismatic. Then we say this configuration, we name this configuration from the base of the robot. Here the base is revolute, and this one is prismatic, and the second one is and the third one is prismatic. Then it is revolute, prismatic, or RPP. Another configuration is about spherical configuration. It is RRP. Then the first 2 joints are revolute or rotational RR, and the second and the third one is prismatic. Here are some figures for revolute. The first one is revolute, and the second one is also revolute, and the third one is prismatic. Then we say it from the base. We name it from the base. It is RRP. And another configuration is revolute configuration. It is RRR, 3R. And here we can see that the first one is actually here the base is R, revolute, and the second one is rotational or revolute, and the third one is revolute. And here also the first one is revolute, the second one is revolute, and the third one is revolute. We say it RRR. It is RRR configuration. For example, for a special type of revolute configuration, we have a KUKA robot. KUKA robot can be used for surgical and medical applications in the hospitals, in the surgical actions and the surgeries. This KUKA robot is very famous in the industry. Also, we have another configuration. Its name is Iskara. Iskara has RRP configuration, Revolute, Prismatic. Here we can see that the base is Revolute, and also the second one is Revolute, and the third motion is Prismatic. Here we say Revolute, Prismatic, RRP, and it is and this figure is for Iskara robot. Iskara is selective compliance assembly robot. About robotic arms and the robotic manipulator, actually various disciplines are used, such as mathematics, physics, biology, electrical engineering, mechanical engineering, chemistry, and computer engineering, computer science, and different types of disciplines, different types of fields are used. It is because that we need to design the mechanical parts, the control part, and also we want to use different types of sensors, actuators, and other types, and for computer programming and doing some calculations. Here, actually, we have different types of robotic manipulators. We start from the base of the robotic manipulator. We have a manipulator linkage and mechanical parts, and also we have to use a controller, a suitable controller, a linear or non-linear, a robust controller for removing the or facing with the disturbances and the uncertainties in the robots. And also we have some actuators and the power conversion unit and the sensors and user interface. Actually, with connecting or by connecting these parts, we can use the robotic arms or robotic manipulators. Here we can see that we have different types of robotic base. The first type is fixed robot, and the second type is mobile robot. We have two types of the base, and this one is for the fixed robot, fixed base. The base of this robot is fixed, and this one is mobile. Also, we have different types of sensors or sensing devices, such as vision sensors, such as infrared sensors, ultrasonic sensors, force sensors for the for using in the grippers, and actually in the effectors we use some force sensors, and we have different types of sensors. And also for actuators, we can use different types of actuators for the devices, such as synchronous motors, stepper motors, AC servo motor, brushless DC motor, or brushed DC servo motor. For different types of motors, we can use some actuators. And about the controllers, about the control input, we can actually use different types of boards, such as RoboBoard, robotics controller, and the basic stamp to model, and different types of interfaces such as converters, ICs, and the different types of controllers, such as DAC cards, data acquisition cards for some interface, and so on. Actually, we have some common uses for robotic arms, such as handling materials, transferring material, loading machine, and unloading machine, and welding. These are some, or spray coating assembly. These are some applications for robotic arms, for example, in car companies and other industries. These robotic arms can be used for different aspects. About the design of the controller, actually, at first, we needed to know the structure of the robotic manipulator. It is required to know the dynamic model of robotic manipulator. What is the dynamic or dynamical model of the robotic manipulator? And the second step is to define the tracking error. Actually, we saw in the control loop, we need a tracking error. The third step is for design of the global sliding surface. Here, we want to know about a robust control method based on the sliding surface, sliding mode control, for designing a suitable controller for the nonlinear structure of the robotic arm or of the robotic manipulator. The fourth step is about designing a control input, a suitable, robust control input for the robotic arm. And the fifth step is for adaptation law. If we have some uncertainties, some external disturbances in the system affecting the nonlinear system, we need to design an adaptation law, a suitable adaptation law for robotic arm. And the last step is for implementation of the controller, of the robust controller for robotic manipulator. These steps are done for having a tracking action, for tracking purpose of the robotic arm, of the robotic manipulator, and also for actually removing or eliminating the disturbances or perturbations. Here we see different structures of the robotic manipulators, and for all types of robotic manipulators, we can use this Euler-Lagrange formulation, which is introduced by Sponga and Vidyasagar in Robot Modeling and Control book. And for the Euler-Lagrange dynamic model of N-link robot manipulator, this equation, BQ is a matrix, is a n by n matrix, is multiplied to the acceleration vector q double dot plus CQ, and Q dot is another matrix, is centripetal Coriolis matrix, and it is multiplied to the vector of velocity Q dot plus GQ. GQ is the derivative vector, and this equation is equal to UT. UT is the control vector. It is a normal equation for robotic arms or robotic manipulators in the robotic systems. And you can find this equation in all robotic books or robotic scientific papers. And also with some calculations, we will have this model in the presence of actually friction and static friction, FAS and the Thaldy, and we can see this model. And finally, by dividing the BQ to B0Q plus delta BQ, B0Q is the null part of BQ matrix, and delta B is the unknown part of the BQ, or with the uncertainties term. We will have this equation, the fifth equation, like this, and NQ and Q dot will be CQ Q dot multiplied to vector of velocity plus GQ. Finally, after some calculations, we can find Q double dot. Q double dot will be minus B0Q inverse multiplied to this term. Here we can see that the acceleration vector will be this term, which contains some known and unknown parts of the robotic arm, and also the control input. UT is control input. Here, finally, for designing of the suitable sliding mode controller, we use this equation. Q double dot is a vector of acceleration is F0 plus B0 inverse UT plus DT. DT is the actually some disturbances, external disturbances and unknown parts, and some uncertainties in the model. They are combined in the DT term. It means the lambda uncertainties and the external disturbances, and the F0 is the bounded nonlinear function. Then this model is the final model for use in this presentation, and ET is the tracking position error, which is difference between Q, the position of the robotic arm, robotic links, and Q desired position. Then we have this tracking position and the tracking velocity, E dot. E dot is Q dot minus QD dot. Then QD is the position, desired position trajectory, and QD dot is the desired position, desired velocity trajectory. Then we can use this sliding surface, ST. ST is the sliding surface for actually, if here we want to here, if the error signal the initial error if is here E0. And if we use this linear sliding surface, if it is linear sliding mode control, for the linear sliding mode control, we use 2 steps for converging the error signal, the tracking or tracking trajectory to 0. Actually, here we have the first step. Here is reaching mode. Here is reaching mode, and the second one, and the second step is sliding to origin, to 0. Here, if we use this linear sliding mode control, and we want to converge the tracking errors, to converge E from initial state to 0 to the origin. Actually, we will have the reaching and sliding modes or steps. However, in this global sliding mode controller or global sliding mode surface, actually the sliding surface is nonlinear, is like this. And we do not have the reaching mode. From the initial state, from this initial state, from the first moment from here, the sliding motion will start. The sliding motion will be like this, the origin. Then here only we have sliding motion from the initial instant. Here we see that we do not have reaching mode. We do not have reaching mode in the global sliding mode control. However, in the linear sliding mode control, we have 2 modes, reaching and sliding mode. This is the idea of this sliding surface. Using some time derivations or differentiating the sliding surface, we will have a stat, and using this stat, we can find the control input. The control input finally will be a stat if is equal to 0. Finally, we can find UEQ, or equivalent control input will be the signal UEQ, or equivalent control signal. And using auxiliary input, we will have some sign function in the auxiliary control input. And using UEQ and UIUX, finally we will have the total control input like this. U will be UEQ plus UIUX. UEQ can be found from a stat. If a stat is equal to 0, S is the global sliding surface, and the stat is the time derivative of the sliding surface. And using this function, we will have UEQ, and UIUX is the nonlinear part of the control input, which is used for removing the disturbances. Here we can say that if gamma is bigger than a norm of dt is the perturbations, some uncertainties and disturbances in the model, and the gamma is bigger than norma of dt, then gamma hat is the estimation, is the estimated value, is the estimation or the adaptive law for estimating gamma. Then gamma hat that will be kappa multiplied to norm of ST G transpose. Then using this gamma hat that here, we have gamma hat that equal to this one, and with integrating gamma hat will be produced. Here we have gamma hat is equal to kappa integral of this term. And finally, using UX and also this gamma hat, finally we can see that the IUX control input will have two parts. The first part is the proportional term, and the second part is the integral term. Then it is in the type of PI controller, and it is a PI type global sliding mode control. Here we can see that it is P proportional, and this part is integral. Then it is a PI type global sliding mode controller. And here we have a theorem about global sliding mode control. And here we have the control input, the total control input using the adaptive law. And finally, using this control law, we can see that by using the Lyapunov function, such as Vt by two terms, sliding surface and gamma tilde is the error of the adaptation law, such as gamma tilde is gamma hat minus gamma. Finally, by some calculations, we can see that V dot will be finally a negative term. It is minus minimum of this term multiplied to this term, and it is minus this finite time condition. Actually, this is finite time condition for the Lyapunov functions. And if we have this condition in the Lyapunov function,
Professor, the time is for 4 minutes only.
Okay, thank you.
Yeah.
I'm finishing this part, and finally using some this control input, we can use the proposed control method for two-link elbow robotic manipulator, like this robotic manipulator. And we can see that we have a tracking purpose here. We have Q1 and Q2 tracking these are the paths for two-link robotic manipulator. And here we have a precise tracking purpose for this robotic manipulator. And these are some sliding surfaces, and also the control inputs are converging to the origin here. And also we have a three-link robotic manipulator. Q1, Q2, and Q3 are for 3 degrees of freedom robotic manipulator, which are tracking the reference signal. And the sliding surfaces are converging to the origin, and the UAT U1, U2, and U3 have the suitable amplitude in the signals. For the practical use of this controller for the robotic manipulator, actually, we have inverted pendulum, rotational inverted pendulum, which in the rotational inverted pendulum, also we can have some tracking purposes and also stabilization for the rotational inverted pendulum. Thanks a lot. Thank you for your attention. And if you have some questions, I'm ready to answer.
Okay. Thank you, Professor, for the incredible presentation. So I would like to resume this presentation. So this robot manipulators is one part of a control system, which controller, actuator, sensor, and also this robot manipulator have 5 system: PPP, RPP, RRP, RRR, or SCARA, RRP. Professor, 6 step the design of this robot have strong basic mathematics. So we have to strong basic mathematics for to understand this control system. So for the session for discussion, please, if the audience have a question. Okay, from me, there's a question, Professor. You presented a rigid manipulator. What about the soft manipulator? Are they differently? And what kinds of criteria between soft and rigid manipulator?
Actually, for the soft manipulator, we name it flexible link robots. Actually, for the flexible link robot, the dynamic model of the manipulator will be very, very complex, will be very difficult than rigid robotic manipulator. In the new papers, in the new sciences, some researchers investigated about flexible manipulators. Actually, some of the dynamic models of the rigid robotic manipulators are not useful for the flexible link robots. For the flexible link robot, the dynamical model will be different. Then we can find some of the models of the flexible link robots in some papers. However, they are not so accurate because the degrees of freedom in the flexible link robots are more different, and you can assume that the flexible link robots have a very hard mathematical model than rigid robotic manipulators. Then the problem for the flexible link robots are so different. We do not study here for the flexible link robots.
I see. For the rigids only, we see complexity enough to design this robot rigid manipulator. The flexible is more higher, complex.
Of course, yes,
Yeah.
of course.
Yeah.
In the presence of some disturbances and uncertainties, and also in the presence of input saturations with some other constraints, the rigid robotic manipulators are so complex. However, for the flexible link robots, for the flexible links, actually the complexity will be so higher than rigid robotic manipulators. And the investigators and scientists work on the new aspects of flexible robots these days. Actually, in face of the disturbances and the uncertainties, and it is still open problem. It is still open, this feature.
Can you give next some examples of for rigid and flexible manipulator application? Maybe in surgical, semiconductor, or nuclear radiation?
Actually, flexible links are more useful in spacecraft. For example, in flexible spacecrafts. For example, an example for flexible links in spacecrafts is that assume that you have a camera. You have a camera in a spacecraft and or in a satellite. Actually, you want to use that camera for some pictures and some recording some movies from the Earth, and you use that camera in the links, in the flexible links of the spacecraft or other aerial vehicles, and if the links are flexible, it is required that you control the flexible links of the spacecraft such that we have no disturbance or no perturbation in the movies of the camera. It is a spatial aspect of using flexible links in spacecraft and recording some good quality movies in the camera.
Yeah. So whether dangerous control such as nuclear radiation detection still match for the rigid manipulator.
Yes, in the nuclear applications, actually the rigid manipulators are used. However, if the lengths of the links, are too much, in all of the applications, they can be assumed as flexible links. We can say that based on the length of the manipulators or length of the links, actually, if, for example, the first point of the link moves theta degree, or for example, we have a movement in the first part of the of a link, and we can see that in the last part of the link we will have a difference in the movement. We can assume flexible links for some robots with some rigid robotic manipulators with high lengths.
Okay, the next question may be from the audience. Please raise your hand. Ms. Fitri, can you help me for the question?
I think maybe because the time is up, almost done, so I think maybe the session will be end up.
Okay. Thank you, Professor, for this presentation, for this opportunity to discuss in this afternoon. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much for inviting me to this presentation. Have a nice day. Thanks a lot from the students and you, and also Dr. Sambas for inviting me to this presentation.
Yes, sir. You're welcome. Thank you so much.
Thank you, Professor.
Thank you. Thank you. Bye.
Yeah.
Bye. Well, thank you for Mr. Gunawan Reviadi that already moderate us today and lead to the discussion session, because this is the last part of our virtual lecture. We finally come to the ending of this part. So before I close this virtual activity, I'd like to thank so much to the speaker also, Professor Saleh Mobayen, for the informative and interesting presentation. Also, thank you for UMTAS, International Office, all dean of the faculty member, and all head departments, also to the participants and all students, also for the distinguished guests. Hopefully, this virtual lecture will be beneficial for everybody. Amin. After this, maybe we will have some photo session. So don't leave so soon. You can open the video and also stand by there. I am Sulidar Fitri as the MC. Beg your pardon for the mistake we have made. Thank you very much. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Oke, photo session.
Kita punya berapa page di sini?
4.
Oh, 4.
Iya. Mau sama siapa, Miss?
Dari situ bisa nggak, Pak? Punya saya low connection.
Oke, bisa. Oke, first, then second, next. Okay.
Well, thank you for everyone. See you again in the next occasion, maybe in the next series of the lecture.
Thank you very much.
Bye-bye.
Thank you. Bye.
See you.
See you.